Okay, hello everyone. Sorry for not being able to hold a problem session live this week, but I wasn't feeling very well. I'm feeling better now. And so, what I'm going to work on with you all is this last part of the first homework assignment when we're looking at the bias variance trade off and where errors in our model come from. And so hopefully you're familiar with this expression here that says that the error of our model at some test point x naught is equal to the bias of the model squared plus the variance of the model squared plus the irreducible error of the model. And so let's just recall what each of those things is. The bias of our model is basically the difference between the expected model. Recall that when we're training a model, we get training points that are distributed in our domain, and we get the associated output to those training points. And this all happens probabilistically. And so if we look at all of the outcomes we could possibly get and average them, that gives us an expected model. And the first bit of error that's introduced into our predictive regime is by just the fact that this model might not actually be able to represent the ground truth. We can see that if we have just a linear model and the ground truth is some sort of sinusoidal function, then a straight line can't accurately predict a sinusoidal function, and so we will have a bias, an inability of our model to actually capture the true underlying ground truth. The next thing that we will get is the variance of the model, and this is we have our expected model, what we expect to see given our training regime, but then we also have a deviation from it. We're not going to see our expected behavior every time. We're going to see the behavior that we get, the difference between that and the expected behavior. And then we see the expected difference between our model and the expected behavior of the model squared. That's the variance. And the final source of error is the irreducible error, which is just the error that comes inherent to the predictive task that we have. If we imagine this, our y value, the quantity we're interested in predicting, is some function of the features we have access to plus some random noise, we're always going to introduce a little bit of uncertainty because of that random noise, and there's nothing we can do about it. And when we sum up these three quantities, we get the total error of the model. And so we were asked to show the compare the flexibility of a polynomial model with a test error decomposition, which is expressed in this form. And so I'm just going to walk you through how to go about doing that, hopefully to help you get a better feel for what these quantities are, and also to help you get more comfortable using Python to do these types of computations. So here we go. The first thing we're going to do is we're going to create a function that can create us some sample data. We're going to be working in the same regime that we have been so far in this class, where we're going to have a simple function of x to give us our y values plus some random noise. So I'm going to call this function create sample, and it's going to take in a function f and a number of points. What we're going to do is say that my x values are going to be randomly distributed along the unit interval 0 to 1, And how many of them are we going to have? Number of points, many. Our y values are going to be my function f of x plus random Gaussian noise. Notice here there's this n appended here. That gives us a normal random variable instead of this, which is a 0, 1, or a random variable distributed uniformly on 0, 1. And here we want n random normal variables to add to our function, so we get independent noise defining our y, and then we're just going to return our data. So this will create a sample for us when we need it. So far it's just a function, it hasn't done anything yet. The next thing that I know we want to do is we want to define polynomial features. So we're going to be fitting polynomials, and to do that we need to create the constant term x, x squared, x cubed out of our training data. So I'm going to define a function called polynomial features, and it's going to take in my training data and the degree of the polynomial I want. I'm going to do this in the quickest way I know how. So here, m is going to be an array starting at 0 and then going up to the degree of the polynomial. And then I can define my polynomial features with this syntax, which allows me to turn my one-dimensional vector of x values into a two-dimensional array. And I just am copying all of those x values into a new axis. And then I'm raising them to these powers m, and that will give me an array of polynomial features. And I can just say return x poly here. And to see that that works, we can define some x values on 0, 1, 10 of them. And we see this is an array of x values from 0 to 1. And then if we said poly features on this, and we said I want a degree 2 polynomial of these features, we see 1, 0, 0, 1, 0.11, 0.0123. We're seeing that this is the x to the 0, x to the 1, x squared. So this function poly features is doing what we want. Okay. Next, what I want to do is I want to find out what my expected model is. And this is something that is hard to calculate explicitly, but is not hard to simulate, or can be simulated with a relatively small amount of work. So what I'm going to do is I'm going to generate models over and over again. And so to do this, I'm going to define a function. It's going to be called the generate models function. It's going to take in a ground truth f. It's going to take in the number of models I want to generate, the number of training points for each of those models, and the polynomial degree I want each of those models to have. What I'm going to do is I'm going to set up a number of empty models to start with. And because normally scikit or sklearn fits the intercept for us, but we are using this polynomial feature that includes the column of all ones, we're going to be fitting that intercept manually. So I'm going to say set intercept to false here when I'm defining these models. And this syntax here just creates a list of untrained models for me. And then all I have to do is for each model in my list of models, I'm going to define some training data. is I'm going to create a sample from my function f and my number of training points that I want. I'm going to create the polynomial features from this training data x of the correct degree, and I'm going to fit my model to those polynomial features and my output data. Okay? And then I'm just going to return that list of models. So once I call that, that should generate a list of models for me fit to polynomial data, all produced in the same way. Okay, and I'm going to define one more function for myself before I really get calculating. And this is going to be the get expected model function. And so I'm going to take a list of models and then I'm going to average out their behavior. Okay, so I know from this list of models, I want to get the degree of the polynomial that they're using. To do this, I'm going to look at the first model in my list just to represent the whole group. A polynomial model, you can access the coefficients of the polynomial by using this attribute of the object. That gives me a list of coefficients. I can look at the length of that list of coefficients, and I can subtract 1 because we have the 0th to the mth coefficient, so the polynomial degree is length of the coefficients list minus 1. I can then collect all of the, or create a space to collect all of the coefficients from all of my models by defining an array of zeros, that is the length, whose numbers of rows is the number of models that I have, and whose width, the number of columns, is the degree of the polynomial plus 1. And then what I'm going to do is I'm going to iterate over all of my models. I am going to, in the ith row of my array of all coefficients, I'm going to save the coefficients from that model. And then what I'm going to do is I'm going to average the coefficients of all of my models. And so that I'm averaging the coefficients over models, I'm asking NumPy to average all the coefficients over the 0th axis, the first axis. And I'm going to return a polynomial object from NumPy using my mean coefficient. So this is just going to give me a polynomial that I can evaluate representing my expected model. The reason that we have to do this averaging process is because up here we're asked to find an expected model. And this is tricky to do analytically. You've probably seen that we're doing some sort of matrix inverse, and taking the expectation of a matrix inverse is just a mess if we were to do it analytically. But we can do it numerically and get a pretty good estimation of what the expected output is. If we just have enough iterations, enough examples of a trained model, we can average those models relatively easily. Okay, so now that we've set ourselves up for success, we can do the actual calculation we're interested in. Let's define a function, a ground truth function, f. I'm going to do a sine function. So we have a sine function with amplitude 2. I want to train, let's go with 50 models to start with. Each model is going to have 15 training points, and the degree of the polynomials is going to be 4 to start with. We're just going to do this for one model to start with, and then we're going to do it for a bunch of different polynomial degrees in a little bit. And so now let's say models equals generate models of f. We have our number of models, we have our number of training points, and we have our polynomial degree. So this should generate a bunch of models for us that have all been trained on their own data, their own independent data. We can then calculate the expected model by getting the expected model from the models that we just generated. And now what I'm going to do is I'm going to plot something so we can kind of see what is going on here. So I'm going to say, give me some x points on the interval 0, 1, and I want there to be 100 of them. I want to make some polynomial features out of these as well, so that we can evaluate each model. And I want the degree of those features to be the poly degree that we're using. And then I'm just going to plot each of the models and what it would predict for each of those x points. And I'm going to make the color of these lines pretty light gray so that we can see what's going on when I overlay our expected model and also when I overlay the true f. So I can then plot our expected model, and I can set this color equal to black, and I can label it expected model. I can also plot our ground truth, and label it true f. And I'm going to limit the y values that we get, because these models, as they go off to the edges of our plot, are going to get kind of crazy. I want to show the legend, and then I want to show my plot. Oh no, what happened? There's a little error. Oh, I misspelled label. Label. Okay, so there we go. We get a nice plot where we show what the expected model is given our ground truth and the training method that we employed. And then in this light gray, you can see all sorts of models, all of the models that we trained and what their predictions would be. So we see that right here in the middle, we get pretty good coalescence around what the ground truth is, but here near the edges, we get some real wild behavior sometime. Like this right here is obviously not really approximating that sine curve very well at all, but lots of the models do a pretty good job. So the bias is going to be the difference between this black curve and this red curve, and then the variance is going to be the difference between the black curve and these gray curves. It's going to be the average difference between the black curve and the gray curves. So there we have the bias and variance expressed graphically. Okay, cool. Now, to calculate those things numerically, I'm going to define a couple more functions. The first is going to be calculating bias. And this is actually not so bad. We just need to take in a model F. We need to take in the ground truth F, an expected model, and the points that we're interested in calculating the bias at. And then we just need to return our function F evaluated at those points minus the expected model evaluated at those points. So that'll calculate our bias for us. That's very simple. To calculate the variance, we need to do a little bit more work. We're going to calculate variance. Here we need to take in an expected model. We also need to take in our collection of sampled models, and we need to take in the points that we're interested in calculating at. We're going to set up some space to store our calculations. I'm going to call it square deviations. It's going to be instantiated as a collection of zeros, and it's going to be an array of size the number of models by the number of points that we're interested in evaluating at. We can then iterate over our models. And what we want to do is set square deviations in row I equal to the expected model at point XX minus, and then just to make the calculation less cumbersome here, I'm going to go and say, make a polynomial out of the coefficients of my model, evaluate that polynomial on my point or on my list of points, and then take the square of those deviations. Okay? So now we've done that for each of our models, and what we want to do is we're trying to calculate the average deviation across the whole array of square deviations. So we can return the average of the square deviations, and we want to average over all of the models, and those are along the first axis, the 0th axis of our array. Okay, and so now with this we can calculate the average bias and the average variance of our model. So to do that, we can look at a whole range of polynomial degrees. We can define a variable at max polynomial degree. And I tried this earlier, and I think that setting the max degree to 8 gives us a pretty good looking bias variance trade-off plot. We can set the number of training points we have to 50, the number of models we have per training run to 100, and we can remind ourselves that the function f that we're using is this sine curve with amplitude 2. Okay? And so now I want to define a variable poly degrees, and this is going to be an array which goes from 1 to the max polynomial degree plus 1. We're going to have a space to store our average square biases, which is going to be an array of zeros that looks like the poly degrees, and I'm going to make sure that I can store floating point numbers in there. I'm going to create an array to store my average variances. And that's going to have, again, the same shape as my polynomial degrees array. And I'm going to ensure that I can store floating point numbers in there. And my X array, so that we can take an average, is going to have 200 points in it distributed along the range 0 to 1. Okay, now we're going to, for each polynomial degree in this array, we are going to calculate our average, bias, and variance. Cool. Here we go. So for each polynomial degree in our list of polynomial degrees, we can define a bunch of models using our number of models, our number of training points, and our polynomial degree. So we've trained a bunch of models. We can look at the expected model from that bunch of models. We can get the expected model from that bunch of models. We can calculate the square biases from that bunch of models. We can calculate bias from our function f, our true function, our expected model, and our set of points we want to evaluate along. We can then square those values, and then in our average square biases array at the ith position, we can average the square biases across all of the x values to get the average square bias for a polynomial of that degree trying to fit this data. We can then do the same thing with our variances. We can calculate the variance from the expected model and our models, and we can do it at all of these points xx, and then we can average the variances across those points, and we can then save all that information in our average variances array. And so, okay, we have now trained a bunch of models of different degrees, and we've saved their average bias and average variance. And now we can look at this bias variance trade-off. So we can look at we can plot the poly degrees array against the average square biases, and we can label this average square biases or average square bias. We can plot the polynomial degrees against the average variances, and we can label that average variance. And we can plot the polynomial degrees, and this is going to be for the irreducible error of our model. Nothing that we can do can overcome the error introduced by just this noise around the ground truth function. And so here we're just going to get zeros, or we're going to get not zeros, but ones. The variance of our random noise is 1, and this is the irreducible error. Okay. And then we can just do some labeling. So we get the x-axis is going to be labeled polynomial degree. we can show the legend, and we can show the plot. Okay. And we see exactly what we're hoping to see. The behavior that we expect is that our irreducible error is 1 no matter what we do. We see that as our model becomes more complex, as the flexibility increases, the bias decreases rather rapidly. But as the model increases in complexity, the variance, the average variance of the model, also increases. And so the total error is going to be the sum of these 3 things. So we can plot the polynomial degrees against the average square biases plus the average variances plus my irreducible error. And this is the average total error. And we see that this average total error is going to be minimized with in this case it seems a degree 3 polynomial, and it's going to increase as the complexity of the model increases thereafter. Okay, I hope that this was a little helpful in seeing how some of these things are done in Python, how we can use Python and programming to estimate things that are hard to calculate analytically, like this expected model term, and then in turn this expected model variance. Again, sorry about not being able to be there to hold the actual office hour or the actual problem session today, but hopefully this little tutorial was helpful for you, and I will see you all later.